Continuing on with section 1.3. Okay, up above we were talking about simple random sampling and showed some ways of getting that with random number generators, and that method of simple random sampling is the one that we base the math on later in the book. So when we do those future problems, they'll usually start out stating that we began with a simple random sample. However, there are times where people go to other methods, and those methods can sometimes still be considered acceptable. So we want to look at the reasons why that happens and what the consequences are. Sometimes it makes our sample a little better, sometimes a little bit worse, though all of these are considered acceptable alternatives to simple random sampling. So let's jump in and have a look at that. So other acceptable sampling methods. Sometimes people use methods other than simple random sampling to choose their samples. Sometimes a simple random sample is too difficult to obtain, and sometimes the researcher is not willing to leave the representation of certain characteristics up to chance. So when we say that a simple random sample can be too difficult to obtain, that can sound a little bit like a complaint. I'd like to do it the right way, but it's just too hard. And sometimes that could be it, but there are times where legitimately it may be even impossible to get a simple random sample, and we'll look at that a little bit in our next few examples. And when you're in that situation, it shouldn't be surprising that maybe your sample you end up with is not quite as good as simple random sampling. And then there's other moments where we don't want to leave the representation of a characteristic up to chance. Our goal is a representative sample, so if we don't leave it up to chance, then we should be doing something that gives us a better than random chance at a representative sample, and we'll see those examples as well. So here's an example that I'd just like to have kind of floating in the background before we get into the alternative methods. Every few years, Chabot conducts a student satisfaction survey. They decided a simple random sample was not practical, as many busy students would be unlikely to volunteer to come in and spend 30 minutes filling out a lengthy survey form. Instead, they decided to choose whole classes of students and to ask the instructors of these classes to administer the survey to the entire class during class time. To attempt to ensure a good mixture of students from classes of various subjects, they chose classes that were equally spaced throughout the schedule of classes. So the idea there with two things, if they randomly chose students, simple random sample, they could contact them and ask them to come in and fill out the survey, but we can't make students do that. So it becomes a bit of a volunteer survey where people can say no, and people who have really busy schedules are maybe more likely to say no. People who have a complaint they want to get off their chest might be more willing to say yes and do the survey. So it can cause some biases. And then when we talk about equally spacing through the schedule of classes, what we mean there is that maybe we chose something like every 30th class in the schedule. And then if there were 120 math classes and we chose every 30th class, we'd end up with 4 of those. And let's say that in the history department there were 60 classes and we chose every 30th class in the schedule, then we'd get 2 of those. So just a reminder, a representative sample isn't about the same amount of everything, it's in the correct proportion. So if there are 4 times as many math classes as there are history classes, it would actually be good that we had that proportion. I think I said 4 times as many, twice as many I meant. So getting 4 math classes to 2 history classes is right if there's twice as many math classes as history. All right, so let's look at some of the alternative methods now, and we will refer back to this as we go through some of these discussions. So one alternative method is called systematic random sampling, and that's a method of choosing your sample so that the sampled items are equally spaced throughout the population. And there are different ways of creating this systematic, equally spaced process. I'm going to go through one here. Others will come up as you do homework. And the key thing to knowing that something has been done in a systematic way is noticing that there's an equal spacing throughout the population. I'm going to show you how to do that through counting, but that equal spacing can also be through time, every 2 minutes, something like that. So there's different ways to do it. So here's the process of a systematic random sampling when you're trying to sample through the items. So step 1, divide the population size by the sample size and round that down to a number that we'll call k, and that will be our spacing. And then step 2 is to randomly pick a number m between 1 and k. That'll be our starting point. We saw earlier we probably shouldn't do that in our head. We want some random method for that. And then step 3, select the members that are numbered m, m plus k, m plus 2k, and so on. So just looking at that in terms of the abstract steps, that can be a little hard to follow. So let's look at an example to see how that works. Suppose that we had a population with 43 items in it. Maybe those are people, bags of chips, who knows. But there's 43 of them, and suppose that we have an easy way to number them from 1 to 43. Then if we choose 8 numbers using a systematic method, that would represent doing a systematic sample of size 8 on this population with 43 things in it. So if we want to follow these steps to get that done, then step 1 is to divide the population size by the sample size and round that down to k. So we're choosing from 43 numbers, so that's our population size. We're choosing 8 numbers, so that's our sample size. And if you just do the division on that, you get 5.375. You can verify that on your own. And then the step says to round that down to k. So our k is always going to be an integer. So if we rounded 5.375 down, we'd get k equals 5. And according to that, that's going to be our spacing. So when we start choosing our numbers from 1 to 43, we're going to be choosing every 5th number. Step 2 is to figure out the starting point. And it says to pick a random integer between 1 and k. So in this case, that's going to be random integer between 1 and 5. And I'm going to go ahead and use the calculator to do that. And whatever I get from that, that's going to be my starting point. So let's bring in the calculator and see what happens there. So math, probability, random integer from 1 to 5. And who knows what we're going to get? We'll see. Turns out it was a 1 this time. Could have been a 5, 4s, 2s. Eventually anything could show up there. Haven't seen a 3 yet, I don't think. There's one. But whatever we get, that's our starting point. So this time it happened to be 1. I'm going to tell you that that doesn't make for the best example, but when you're doing your homework, if you get a 1, you should do a 1. On this one, I'm going to pretend that what I got on that first try was the 2. So that would be m, and that's going to be my starting point. Again, in reality, you're doing these problems. If it's a 1, use a 1. If it's a 5, use a 5. I just think for the purposes of an example, it turns out a little nicer if it's a number in between. So then the final step is to list your 8 numbers. Start off with whatever is the starting point, so 2, and then keep adding the spacing until you get 8 numbers. So 2 plus 5 is 7. Add 5 again, we get 12. Add 5 again, we get 17, 22, 27, 32, and 37. And that's 1, 2, 3, 4, 5, 6, 7, 8 numbers from 1 to 43 that have an equal spacing where they're all 5 numbers apart. So a few quick notes on this before we move on. If I add 5 again, I get 42, and that is still in the range, but they only ask for 8 numbers, so when I get to 8, I should stop. Some other little things that are worth mentioning is if your first number had been 5.875, there'd have been a temptation to round that up to 6, but the process says to round down. So typically when we round, we use our standard rule, is this digit a 4 or lower, we'll round down to 5 in this case, or a 5 or higher, we'd round up to 6. But here the rule says always round down. So even if it was 5.875, we would still have gone with k equals 5 for our spacing. And the reason for that is that if you round up, depending on what you get as your random starting point, you might get to 7 numbers and go for the 8th and you're above 43. But by rounding down, that's never going to happen. So that's why they have what may seem like a strange rule there to always round down regardless of what your spacing looks like in decimal form. All right, now that we've seen an example of how to choose a systematic random sample, I want to talk about the effects of that on how good of a representative sample we have. It turns out that this method usually produces an advantage, by spacing out members of the sample, you're less likely to get a biased sample. In the Chabot study, where they did every 30 class, we said, that's going to prevent you from getting unlucky and over-representing math or under-representing PE. We should, by that spacing out, end up getting kind of the right proportion, which is always a good idea and a beneficial thing when you're trying to get a representative sample. And a lot of the times, an advantage like that does occur with systematic. So usually if you see that somebody used a systematic method, you see that as a positive and probably improving how accurate their sample will represent the population. All right, so on to another alternative called cluster sampling. This is a method that chooses items that are somehow already naturally grouped together. Even though we're filling in the word grouped, the word naturally is important too. You're not throwing things into groups. Those groups already exist. And with cluster sampling, you're just making a choice. Instead of choosing individual items, I'm going to choose them as bigger groups and get to my total sample size a little faster. So the process is to identify what the subgroups are. That's what we're going to refer to as our clusters. And those should naturally exist in the data set already. So just as a quick example, going back to that Chabot student satisfaction survey as our example, the people who chose people to come in and do the survey did not actually choose people. They chose classes and then gave the survey to the whole class. So they didn't choose individual students. They chose individual classes, and those would be the clusters in that example. They didn't put the people in those classes. The people picked their own classes. So those groups were already naturally existing in the data. And then you randomly choose a sample of clusters, which is what they did in that study. They chose a certain number of classes to get a sample size that they needed. And then you use all the members of the selected clusters as your sample. So in Chabot's student survey, the clusters were the classes. So there was definitely cluster sampling going on in that Chabot student satisfaction survey. But also in the Chabot study, we could say that it was systematic because the courses were chosen equally spaced in the schedule of classes. And anytime you have that equal spacing going on, there was some systematic part to that process. Could have been just like we described or some other way of spacing them out, but if you're doing equal spacing, you have a systematic sample. Okay, so talking about the cluster sampling, that actually is not usually a good thing to see that. It causes a disadvantage. Clusters usually have like members in them, thus increasing the chance of getting a biased sample. And so if you think about that, the class that you're in right now was not randomly assembled. If it's a class during the day, it tends to have younger students than if it was a class during the evening. And we want that mixture of people, but it's just important to realize that when you choose a cluster, you're more likely to choose 2 night classes and get an overrepresentation of older students than to have that overrepresentation if you just chose students one at a time. Because whenever you choose something, you choose a whole cluster of it at once, and that can cause problems depending on your luck. Essentially, cluster sampling is kind of like having a smaller sample because you're making less random choices. So if I want 600 students and I choose 600 students individually, I'm making 600 random choices. And the more random choices that you make, the less random variation ends up in your results and the more representative your sample gets. So here we may still get to those 600 students, but we might do it choosing only 12 classes. And that smaller amount of random choices creates more random variation in our data. And when there's more random variation, you tend to have larger amounts of sampling error. So we get a bit of a disadvantage from cluster sampling. If for some reason we have to choose in clusters, we should probably go with a bigger sample size than we would normally have chosen to try and end up making more random choices in our clusters and squeezing out that random variation a bit. All right, the final alternative is called stratified sampling. And this is a procedure that chooses items from different subpopulations so that they make up the same proportion of the sample as they did in the population. The process is to identify the subpopulations in the population that you want to represent. From each subpopulation, obtain a simple random sample of a size that is proportional to the size of the subpopulation, and then use all the members obtained in step 2 as your sample. I'm going to work out an example for you below, but in a way we already did one earlier on in the notes when we talked about trying to represent the gender in a sample of Chabot students properly. And so when we wanted that sample of size 450 to be 57.8% female, we took 57.8% of 450 and figured out our sample size that way. So we were talking about representing gender there, but in a stratified sample, you were picking one characteristic and making sure you represent it properly. So it's going to be a very similar process. In a representative sample, you would hope that every single characteristic has that proper representation. In a stratified sample, you're still hoping for that, but you're making sure it happens for at least one. And that creates an advantage because you're ensuring that at least one important characteristic is properly represented. And you'll see we're still going to make some random choices, so there's kind of the normal chance of luck affecting all the other characteristics, but on this one characteristic we're going to make sure it happens. So let's go ahead and look at an example to see how that works. Okay, so at Chabot College, 3,332 students are 19 or younger, 4,393 are in their early 20s, 1,859 are in their late 20s, 2,269 are in their 30s, and 3,222 are 40 or older. So how many students should be chosen from each age group if you wanted to obtain a sample of size 250 that is stratified based on age? And I think I didn't mention this up here earlier, but when you stratify, because you have these different age groups, you can also, like if you're studying GPA, you can talk about what the GPA is for the younger students, the older students, the kind of middle age group students. And if you just did a random sample, you might not note age at all and only look at GPA. So that sometimes makes it more interesting when you can make those comparisons. So anyways, let's get at how that's done. So let's start with the group of 19 or younger. So I'll just put 19 and down. And we want to figure out how many students would we pick in that group. So they want a sample size of 250. So I want to take 250 times the percentage of students that are in that age group in decimal form. So they told us what that was before, and we just took that percentage, 57.8, slid the decimal over to 0.578, and did our multiplication. This time the percentages aren't given, so we have to calculate them ourselves. We know there's 3,332 students that are in that category, so what we want to do is take that and divide that by the total number of students, and that would give us the decimal, which we could then multiply with 250 to get our answer. So unfortunately, they didn't tell us how many students there are total here, so we would just add that up real quick. So bringing in the calculator and clear out that random stuff. And adding those up, we find out there's 15,075 students at Chabot at that time. We'll see this officially later, but our population size is usually written using a capital N, so I'll say that capital N is 15,075. Now if I make that the denominator right here, then doing that division is the same as calculating the decimal form of the percentage. So let me just show you that piece real quick. So the 3332 divided by 15075 is 0.2210281924. We'd usually say that's about 0.221 or 22.1%. But as soon as I shorten that, I'm rounding it and bringing in error. And so after I multiply, we would round again. And it's not good in a process to round more than once because then you bring in error more than once. So the best idea here, instead of going to the decimal, is just taking that 250 and multiplying it immediately by the fraction and going straight to the decimal form of how many students we want in that age group. So it's saying about 55.26. As we discussed earlier, sample size always has to be a whole number. So how many students would we choose from this group? You just go with the nearest whole number, which in this case would be 55, because the 2 we would round down. So that's how many students we want in the 19 and under category, and then we just keep doing that for all the age categories. So in the early 20s, 20 through 24, we still want to do 250, and we still want to multiply by the decimal form of that fraction. So let's see what that would be. Take 4393 for our numerator. The 1505 will stay, and do that calculation. We'll find out how many students we need in the early 20s. You could just type the whole thing in again, but a nice little trick on the calculator. If you hit second and then enter, it'll bring up your last calculation. And since 2 of the 3 numbers stay the same, we can just leave those alone and use the arrow keys to move over our numerator, change it to the new number, and press enter. And we don't have to retype everything. So that's kind of a nice little trick. So that's about 72.85. And if you were to round that to the nearest integer, you would get 73. So now we just need to continue with that process until we get all 5 of those age categories done. So we'll just run through those now. So let's go ahead and write out the next 3. So now we'd have our upper 20s, 25 through 29. So set that up the same way, 250 times, for that group, this is the number, 1859 over 15075. And we'll figure out what that one is in just a moment. Let's go ahead and set up the other ones for the students that are in their 30s. We have 250 times, same idea again, and there's the number for the 30s. So 2269 over 15075. We'll do that one. And then finally for the people who are 40 plus, 250 times, and there's their number, 3222 over 15075. So let's just bring in the calculator and knock all 3 of those out at once. So again, just editing the ones we've already done before. So for this one, we want to change this to 1859 for those students in their upper 20s. So that gives us 30.83 roughly. And rounding that, we would say we should get 31 students from that group. Going to those in their 30s, we would change this number to 2269. So we have about 37.63, which rounding to an integer would be 38. And then going finally to those 40 and above, and changing that to 3 and then 2s. And for that one to get 55.43, which would round to 55. So that's it for every one of those. One final step that you want to take on these would be to add them all up. I just noticed something a little strange, that I have the same answer for both of those, and that shouldn't happen. So I feel like I must have typed this one in wrong or that one in wrong. So let's see. I'm hitting second enter here. You can go back through your old calculations. So what was that one? 55.25. And then, oh, the one I just did I had wrong. Sorry about that. So 53.43. Video proof that I'm not perfect. There's the 53. Okay, so now the final step would be to add all those up. So 55 plus 73 plus 31 plus 38 plus 53 is 250. And that is the size that we were supposed to get. So that all works out perfectly in terms of the sum, and that's kind of what we hope to happen. So there are occasions where it doesn't add up total, that doesn't total up to what it's supposed to be, in this case the 250 that they asked for. So I'm just going to throw a couple scenarios at you. If this was a 251, that would happen because we rounded up more than we rounded down. And what we would need to do is find one of the ones we rounded up and round it the other way so we get the right total. So just assuming for a moment that happened and I had to pick one of the ones I rounded up and round it down instead, that would come from these three. And what I would look at is which one was closer to rounding down, which would have been this 37.63. So if my total was too high, I would have picked this one and rounded it down to 37. If the total was too low and I needed to round an extra one up, I would look at the ones I rounded down and say there would be less error in rounding a 4.3 up than rounding a 2.6 up, and I'd make this a 54 instead of a 53. Most times it works out like it did here, where you get the right total. If the total is wrong, though, then we would fix it by picking one and rounding it the opposite way to make the adjustment, and you try and pick the one where rounding it the opposite way creates the smallest amount of rounding error. So hopefully that won't happen to you, but if it does, now you know how to handle it. All right, that wraps up section 1.3.